So my name is Jackie. You can also call me What a Merger Jr. So my snappy title for you is using the VLA to see VLA, so the Very Large Array of Radio Telescopes to see the largest things in the universe that we can actually see, which are galaxy clusters. I originally wrote this talk for Astronomy on Tap San Antonio, and because they are so close to the Southwest Research Institute, which is involved a lot more with space science, NASA missions, these types of things, a lot of their speakers give beautiful pictures of moons and things like this, and then I came in like, oh, here's a dark matter simulation. So I had to give them a lot of building blocks, but y'all are a very seasoned audience, so I don't need to give too much of that, but I'm gonna kick it up a notch for you guys. But nonetheless, I decided to keep this structure for the talk, which I would like to answer a few fundamental questions about astronomy and science in general before I actually build up to what I study for my thesis. And the reason for this is that I spend most of my day feeling very stupid. I might be the stupidest one in my department, maybe the university, possibly the whole world. But when I sat down and thought about this talk, I thought, well, maybe I'm not that stupid because I can at least answer these simple questions, existential questions like what is dark matter and how can we see back in time, which I'm sure you think about over your morning breakfast. So we'll just get right into it. The first question, very easy to answer, is what is dark matter? So here's a dark matter simulation made by some mathematicians who are a lot smarter than I am, basically showing you the entire universe in only dark matter. So we're going forward in time. You'll notice that in the beginning, everything sort of looks like the same. If you ever take a graduate class, you too can chant like a drone, homogeneous and isotropic, like we did. But over time, things start to cluster together. So you're looking at regions of higher density in those white spots, and the orange bits are voids where you're not really seeing too much of anything at all. And we think that the universe largely looks like this today when you look at the dark matter. We think that baryons, the stuff that you can actually see, does follow this same track, but this is sort of our theoretical basis because the dark matter is the easiest part to simulate because it only interacts with gravity. So that's a lot easier to code, and you can actually build a computer that can do that. So there might, for instance, be a galaxy cluster at the center of that giant white thing in the middle. Do I have a laser pointer? I really do. Wow, okay, so there might be a galaxy cluster there, so let's dive right into that. That's all I'm gonna say about dark matter, so I hope you enjoyed your vision of the cosmic web. The end. So, question 2, what is a galaxy cluster and what do we actually find inside of them? So here's an actual astronomical image of a galaxy cluster. You're seeing some beautiful optical stuff going on here, and then these white contours are very hot X-ray emission, and I'm going to explain that in a moment. This red thing is showing your brightest cluster galaxy, which tends to be your most massive and brightest galaxy in the cluster, hence brightest cluster galaxies. We're very creative. So there you have it. That's what a galaxy cluster looks like, and the majority of these things are not so far away from us in, cosmological terms, but let's just back up with a nice schematic. So here is basically everything in the universe. So your blue cloud here is a dark matter halo, and it's sort of its own thing. When I was showing you that simulation, you were seeing multiple dark matter halos collapse gravitationally over time. So around a cluster, you're going to have this really, really massive dark matter halo, and then inside, you'll have your constituent galaxies, which sort of follow this cosmic web-looking thing. So all of these lovely clip art things are galaxies. In the center, and in other places in the cluster, you might have a supermassive black hole. This red stuff is showing you that really hot X-ray emission that I was showing you. We call this the intra-cluster medium because it sort of goes in between the member galaxies. And this is sort of the smoking gun if you want to find a cluster nearby. And it's something that is unfortunately, curiously absent in the things that I want to look at. So, of course, my life is a bit more difficult, but we'll get to that. Zooming in on one of these member galaxies, you have all the stuff that you can see with a telescope, right? You're going to have stars, gas, dust. That gas is made up of a bunch of different stuff. Loads of people have come and talked to you about the hydrogen in there. And you have nitrogen and carbon and all these things. But there's a special gas that I'm going to focus on, but I'll keep you on the edge of your seats for which one it is. And then you have our really cute dust bunnies. So, like I said, a lot of the galaxy clusters that are out there in the universe are relatively nearby to us. So they're pretty much all characterized by very similar qualities. And because the universe kind of sort of evolved uniformly, the clusters are all going to look like this when you're looking at redshift 0 to 1, say. The thing that you can remember about a galaxy cluster is that it's massive, passive, red, and dead. So the massive bit, because it's formed most of its stars already. Passive meaning you're not having these massive mergers, you don't really have things really like running around doing too many crazy things. Red, because most of their stars are red, so the hotter, bluer ones will have died off already, and you just have these red, cooler ones just sort of existing for all of eternity. And dead, because they're not forming any new stars. And because you can find that hot X-ray emission, the life of galaxy cluster searchers at redshift 0 to 1 is slightly easier than mine. But my question that I'm spending 6 years of my life answering is, how did they actually get here? So you have your really smart theorists who sit in a room and think really hard on their computers about what happened with dark matter, and you have really smart people who use their X-ray telescopes to see galaxy clusters. But what happened in the middle? Because we can't see the Big Bang, but we do know that there must have been some evolutionary point in time where you would have the prototype of a cluster or a protocluster, where maybe things were the opposite of massive, passive, red, and dead. And so my work is basically trying to find those things. So in PhD terms, it's how do large-scale structures form, and what kinds of galaxies live in the progenitors to a cluster? Are they different than a cluster? How do you actually find a dead galaxy that's not forming any stars versus a very active galaxy? And does the dense environment of our protocluster actually affect how the galaxies inside are behaving? So we've got 2 questions down. Now let's actually dive into what you can actually observe, because that's a real nice way of sitting around thinking about astronomy, thinking you have the whole universe solved, but now you have to actually propose to a telescope and hope that you get data. And if you're me, your proposals won't be accepted. But if you're someone else, maybe they will. And you can look in any wavelength you want. So here's the full spectrum, right? At the very high energy end, again, you're going to have that intracluster medium if it's there. You have things like supernovae, supermassive black holes. And then go into longer wavelength, you're going to have your stars in the visible and the near infrared, and then you start getting into some of these gases out here. In the further infrared, you have excited carbon, you have the dust continuum, and in very far radio, you'll have neutral hydrogen, you can get magnetic fields, all kinds of things. But the very special gas that I alluded to is carbon monoxide. It's a really special molecule. I want you to keep in mind, before I go any further, something special about what these telescopes are doing as you get to longer and longer wavelengths. I did talk in great detail about this a few years ago, but I'm going to give you a refresher because I don't know why you would have kept that in your brain for 2 years. So, if you want to find a star-forming galaxy, there are a couple of things that you can think about. We think that protoclusters are probably characterized by extreme star-forming galaxies that don't live for very long, but while they're around, they do a bunch of crazy stuff. So they have a lot of gas, a lot of dust, and the most extreme of these are so dusty you can't see them in visible light. So again, very creatively, we call them dusty star-forming galaxies. But the weird thing about them is that we actually didn't discover the first one until like 1997 or 98, meaning that for a really, really long time, we were missing a good like half of the universe. Like, I think that's kind of creepy if you think about it, that there was just like all this stuff out there and we were looking up at the sky and we just like weren't seeing it, but it was there. So basically what was happening was the dust was absorbing all the starlight. So in visible light, there's a bunch of stuff that you're just not going to be able to see. But the dust is super, super bright. So you go to longer wavelengths, now you can see the dust. You can use the dust for a couple of different things, but what I'm most interested in is, of course, this evolutionary pathway. How are these galaxies actually forming their stars, assembling their mass, collapsing into the galaxy cluster that we see today? And in that sense, I want to know about its potential for the future. What is it going to do after today. And the way you do that is by looking at its gas, specifically its molecular gas. And that is going to tell me how many stars it's able to form over what time scale. And then I can actually map out a nice timeline for my galaxies. So this is how you make a star. This is all I know about how to make a star, so please do not direct your questions towards this slide. But you start with a cloud of atomic hydrogen. At some point, these hydrogen atoms come closer together, and you have molecular hydrogen, H2. And then through some processes, these clouds collapse. Question mark, profit, star. The end. This is all I know. But of course, nothing in life can be that simple. We do need carbon monoxide. Why? Because molecular hydrogen obviously photodissociates, meaning that if you shine a light bright enough on it, you will just break it apart, which is very sad times, and kind of gives you a hopeless case for ever forming stars ever in the universe. But luckily, carbon monoxide is here to save the day. It is a much larger, stronger molecule, and you sort of get this shielding effect where you have a cloud of molecular hydrogen, and you also have a cloud of carbon monoxide. It just is this lucky, ubiquitous thing that where there's H2, there's CO, and a bunch of people will sit in a room yelling and screaming about what the actual ratio is. Is it 1? Is it 4? Is it 10? I don't know, but some other people in their papers tell me what that ratio is. It's empirical, basically. You just have to calibrate it using nearby galaxies. And now, basically, the math is I see how bright the carbon monoxide is. Now I have a massive carbon monoxide. Now I have a massive H2. Boom. Now I know how many stars it can form. Okay, so we're moving along. Now, how can we see back in time? I gave this whole spiel on redshift in San Antonio, but I trust that y'all know what it is. Just a brief refresher, this was originally called the wee-woo effect. But, like I said, you guys are seasoned astronomers, so we don't have to go through this too much, but you got the Doppler effect, things are moving away from you. So, you know, an ambulance gets closer to you, it goes woo, and then it goes away and it goes woo, and because the universe is expanding and everything's moving really fast, we're in a permanent state of woo. So that's redshift in 2 seconds. So the very lucky thing is that the further away you look, the further back in time you're looking. And because we're talking in cosmological scales, if things are 10 billion light years away from you, then you're seeing things as they were 10 billion years ago, because there just hasn't been enough time for the rest of that light to get to you. So if I look really far away, then I can actually witness these galaxy clusters forming with my very own eyes. So my whole shtick is that I'm just going to look for carbon monoxide and hope that I can find a galaxy cluster or a protocluster. And my fun little fact for you is that on Earth, CO emits at 115 gigahertz. A lot of these protoclusters are around redshift 2 to 2.5, which redshifts it all the way into radio. Where my observations take place is 33 gigahertz, which is exactly where your Wi-Fi router is tuned to, which means that I can't use my phone or computer at the telescope. So it's a lovely way to unplug if you ever feel like doing that, but I never do. So, you know, it be like that sometimes, but it's okay. Basically, the point is that around these radio telescopes, you have radio silence for a very large radius. Not a very large array, just a very large radius. So we're coming back to here. I told you about all the information you can get from the full spectrum. Now we're redshifting it. Boom. Okay, now CO is in the radio, and we have to talk about how we're actually going to find it with a radio telescope. So that was your really quick refresher on redshift. Like I said, I knew you guys knew this already. So finally, how does a telescope work? This is Whataburger's favorite part of this talk. So if you were around for the first time I gave a talk on radio astronomy, I had a whole slide about all the radio telescopes that I visited before. And I had this whole shtick about it. Nothing's changed. And in fact, I actually tattooed one on my body. I think it's really cool. I think it's really pretty. But when I go to conferences, I get the same reaction from people every time. And they give me this very confounded look, and they're like, well, I guess no one can say you're not dedicated to your work. I'm like, thank you. I'm going to take that as a compliment. So the thing I wanted you to notice about those telescopes as you went to longer wavelengths is that they were getting larger and larger. And that's because of the issue of resolution. If you want good resolution in your images, then the size of your dish scales as the wavelength you're looking at. So you can imagine for radio, you need a very large dish. So we're not talking about the extremely large telescope, the very large telescope, the overwhelmingly large telescope, which is not a joke. That was real. The unfathomably humongous, larger than the void itself telescope, however, is my own joke. But I could submit this to the International Astronomical Union, and I think they would take it. So you can't use your telescopes that you have in your backyard, and you can't even use something the size of Hubble or the James Webb Space Telescope, which I'm going to tell this joke again, even though I got booed in San Antonio. The James Webb Space Telescope, more like the Just Wait Space Telescope, because it's never going to get off the ground. Oops. But luckily, radio telescopes don't have to get off the ground. All you have to do is put it in a desert and really high up. The only thing that needs to happen is that it needs to be above most of the water vapor in the atmosphere. So something like the Andes Mountains, for instance, is a really good place. But we get around this gigantic engineering issue of trying to build a telescope that is kilometers wide by using this thing called interferometry. The basic idea, without going into too much math, is that you can use the signals from two different telescopes, and there's going to be a slight time delay. You're pointing these two telescopes at the same thing on the sky. The time delay is just related to the speed of light, and you basically synthesize these images through some fancy math. And in the end, you basically, more or less, get an image with the resolution as if you had a telescope the size of the distance between them, which is called a baseline. And I really would like to host this comedy show of astronomers whose baseline is it anyway. So you can imagine taking two, and then maybe you could make 30 or 60 of them. So this is ALMA, the Atacama Large Millimeter Array in Chile. There's 66, I think, of those dishes. And so you combine the signals from every single baseline, and you get these really, really beautiful images. Mine actually come from the very large array, which is even further out in wavelength space. So this is sub-millimeter and millimeter. The very large array is pure radio. For the VLA, they are shaped in a Y. There's 27 of them, but I included the picture of Alma because it's really pretty. It's the one I put on my arm, and it gives me a much better pun, which is, it really is all amazing. So, I just taught you a lot about astronomy. These are all the things I have to keep in the back of my head every day when I'm staring at these images. So the end is looking at a protocluster. So we're looking at a protocluster at redshift 2.5. You're looking at a background optical image, and now I've zoomed in here. These yellow contours are actually the carbon monoxide. The more contours you see, the brighter it is. And I think this one is this one. So this is an image of carbon monoxide in a single galaxy. It has a lot of carbon monoxide in it. Something on the order of 10 billion solar masses is how many stars it could form if it all goes into stars. And then I'm just showing a spectrum here. You can see just how bright that CO line is. So that's all the stuff I've had to learn over the years just to get these images and stare at contours all day and make my brain hurt and my eyes hurt. But I think it's really, really exciting. You know, we've put so many people together to build these telescopes and build the technology to be able to see all these things. And maybe in a few years they'll give me a degree if they like my plots enough. So thank you very much. I will be happy to take your questions.
Thank you. What a merger. We have some time for some questions. Whoa, she explained it so well. Anyone? Oh, there we go. There you go.
The question was, am I working on my PhD? Yes, I'm 3 years into it. I just got my master's this year, so I got X more years. Thank you. Who is this? Oh. Oh, absolutely. Yeah.
How many ALMA proposals did you apply for last time around?
Our group, I think, submitted something like 17. I submitted one. It was ranked in the bottom that you could possibly get. It was in the 4th quartile. It's okay.
It was still probably pretty good. So, sir.
So the question is, what wavelengths does the VLA operate at? And my answer to you is, I've never heard of a wavelength before, because I think in frequency, and it's in gigahertz, sir. No, I'm just kidding. Right, so my band is at 30 gigahertz. I actually don't know how far down it goes, but I think ALMA's lowest frequency is like 100 gigahertz, so it's lower frequency than that.
And how do you convert from frequency to wavelength, Miss Master?
What's new? C over lambda.
There you go. So just in case you guys want to do some mental math. Any other questions? Oh yeah, in the back.
Could you say that louder? You absolutely can. Someone that's not me. The question was, can you actually simulate these molecular clouds? Absolutely. That's an ongoing field of research that's very different from what I do. So I just read their papers and trust them. Oh, great.
And with that, let's thank What a Merger Jr. again.